Okay, so lesson 4, day 2. Yesterday we talked about periodic functions. Today we'll do the stretching, shrinking, and translating of graphs. So let's recall that stretching and shrinking and translations, these are types of transformations. Okay, you learn these in geometry. A translation is what we would call a rigid transformation. It does not change the size or of the function, but when we stretch or shrink, right, in geometry we study these as dilations, so they do change the size of the graph. All right, translations, we'll start with the easy one. The graph of a function is obtained by sliding the original function 8 units horizontally and k units vertically. Okay, so this textbook keeps the change for the vertical translation with the y, but I feel like in Algebra 2, you would have always seen it like this. It always seems we solve for y. So h units horizontally, but remember when we're in our function, it's the opposite of h, and then we keep the same value for k. So when I look at this equation, I'm going to solve it for y first. Now red is my original, and when I look at my rule, because it's a minus, it actually means I'm moving to the right 1 unit, and it's a minus on the outside. I keep that the same, so I move down 2 units. So if we take any point, right, if I take any point on the graph, I'll take this one. If I move this to the right 1 and down 2 units, now I have that point on my image. Okay, so the pre-image is the original, the image is after we've performed some type of transformation. Okay, this is where it gets into a lot. Shrinking and stretching. So dilations, we'll do vertical dilations and horizontal dilations. If we think of our vertical axis is our y-axis. So any dilation is going to be multiplied on the outside of the function. If the multiplier is bigger than 1, we stretch the graph vertically. Okay, so if you check this out in red, that's my original function. If c is greater than 1, okay, so the multiplier out front of the function is a 2, then it's stretching it vertically. It's making it, if you look, it's twice as big. If my multiplier is a number between 0 and 1, it would be a vertical shrink. So the graph in green, my multiplier now is 1/2, and we've compressed the original graph. We keep c positive because let's think about that. If my multiplier were negative, we would then have to reflect the graph over the x-axis. So we could do this, but we really just study the rule first, looking at positive numbers, then we can put all the transformations together. Okay, so we got to check out how the period and the amplitude are changed when we're dilating, when we are stretching and shrinking these graphs both vertically and horizontally. Okay, so when I look at my function in red, my original, so I'm going to determine the period. 1, 2, 3, 4, 5, 6, 7, 8. Right, so from one defining characteristic to another. So when I look at the period for 2 times f of x, my vertical stretch, notice that the distance between the points is unchanged. Likewise for a vertical shrink. The distance between those points is the same. And I have the notes all on one slide for you. So the period of a vertical stretch or shrink is unchanged. And that makes sense. Our period deals with our x values. If we're stretching and shrinking our y values, it shouldn't change anything on the x-axis. Now our amplitude, our height, this is the one that's going to change. So on my original function, my m value is +2. My maximum is +2, my minimum is -2. So when I go to find the amplitude, max minus min divided by 2. So I get a height of 2 units. Okay, so now when I check out my amplitude for 2 times f of x, my maximum point is 4, My minimum point is -4. Max minus min divided by 2. That gives me an amplitude of 4. On my green graph, my vertical shrink, my maximum value is 1. My minimum value is -1. So that gives me an amplitude of 1. Again, I have all the notes on one slide for you. But check this out, if my amplitude is 2, right, the height of my graph, then I make my y values twice as big, well, look at what it does to my amplitude. So whatever my C value is, that's how my amplitude is changing. So my original amplitude was 2. When I multiply my function by a half, that means all my y values are half the size. So my amplitude would be 1. Okay, so take a minute. If you've printed them, then you're good. For your notes, okay, here's everything summed up for you. The period for a vertical stretch or shrink, and I know it's vertical because my multiplier is on the outside, the period is the same. The amplitude, however, I just take the amplitude of my original function and I multiply it by whatever my scale factor, whatever that value of C, whatever I'm dilating by or with. Okay, I just take that y value from my amplitude and multiply it by whatever value I'm multiplying my function by. All right, now horizontal. Our horizontal is always a little bit counterintuitive, I think. So if I go back to my translations real quickly, right, the number on the inside here, so my horizontal translation, it's the opposite of the sign of H, okay, but K stays the same. Well, I sort of have to use that same type of reasoning now when I'm looking at a horizontal stretch or shrink. So first of all, my multiplier is on my X value because it's my X values that are changing. If that multiplier is a number greater than 1, it's actually compressing or shrinking the graph horizontally. Okay, so red is my original. All right, red is my original graph. If I look at my graph in blue where my multiplier is 2, notice that I have more graph now shown. So it's like we've taken the red and think of it like an accordion. We pressed it together along the x-axis. We didn't stretch the top and bottom. We took the left and the right and we pressed it together. If my multiplier, my x, is some number between 0 and 1, it's a horizontal stretch. So I've taken my ends of the graph and I've now stretched them out. So again, go back to the graph in red. Now my graph in green, f is 1/2 x. Notice that there's not as many hills, peaks, and valleys on the graph in green. So it's like I've taken the ends in red and I've stretched them out. Okay, so now, just like a vertical stretch or shrink, we have to investigate how the period and amplitude are changed for a horizontal stretch and shrink. Okay, so I know the graph gets a little bit confusing here. In red, when I go point to point, 1, 2, 3, 4, 5, 6, 7, same period. It's the same graph. Okay? Now, when I look at my graph in blue, when I go from one peak to the next, 1, 2, 3, it only takes me 4 units to repeat the cycle. When I look at my graph in green, I'm going to I can't even. I can't even get there. Okay, let's look. Let me go from here to 1, 2, 3, 4, 5, 6, 7, 8. I've gone 8 units on my stretched graph, and I've only actually gotten to half of a period. Right? To determine the period, I have to go from the minimum value to the minimum value. That's not even included here. So if it's taken me 8 units to get to the middle, I would have to double that, and it would actually take me 16 units here. It's the distance between the lowest value to the next lowest value, it would take me 16 units. So it takes a 16 in order for the graph to repeat itself. So now when I check this out, okay, so if my period was 8, and I'm going to take my x values and multiply them by 2, I don't multiply my period by 2. I've actually taken my period and cut it in half. Right? Because if I go back here, when my multiplier is a number bigger than 1, it's actually a shrink. So I'm compressing. I'm making my x values closer. Okay, so that I actually take my period and I'm dividing it by 2 to get the period of my horizontal shrink. Now, if I take the period of 8, how do I get from 8 to 16? I know that I have to multiply that by 2. Okay, we understand that. But how does it work with the multiplier here? I take my period and I'm actually dividing it by the value of c. Okay, so when my multiplier of x is a number between 0 and 1, I'm stretching it out. So the period should be bigger. Okay, and it's bigger by that same scale factor of whatever my multiplier is. And again, I have all the notes written out for you so you can copy them together. Okay, so now my amplitude, oh, it should say amplitude. So now my amplitude for my original function, my highest y value is positive 2, my lowest y value is negative 2. So same amplitude, right, because I'm using the same graph as my vertical stretch and shrink examples. Oop. I get an amplitude of 2. I get an amplitude of 2. Okay, well, if I look at my amplitude for 2x, my graph in blue, notice that my highest y value and my lowest y value never change. So my amplitude remains the same. Max minus min divided by 2. And likewise, if I have a horizontal stretch, my amplitude doesn't change because think about what we're changing horizontally. Horizontally, we're changing our x values. They're not affecting our y values at all, okay, which is the exact opposite of what happened when we had a vertical stretch or shrink. Okay, so here are our notes for this. The period for a function that is horizontally stretched or shrunk, I take the period of the original and I divide it by whatever my multiplier is. The amplitude for a horizontal stretch or shrink stays exactly the same as the amplitude of my original. Okay, so for the past 2 lessons, I've hit you with a lot of information. Okay, having the notes together, now the next time we meet, we'll be able to put everything together. Thank you for your patience.